civilization is built on the human drive to invent. We take the raw stuff of our planet, the materials that give names to the ages, stone, bronze, iron, and more, and craft them into new forms, expanding our horizons, exploring hidden worlds, and engineering life-changing technologies. Always pushing the limits to be colder, faster, safer, wilder, and now a new era is upon us, where cold is the new hot. Join me on a journey down the thermometer, away from the warm world we inhabit, to the realm of cold. Cold is a force we can harness to save us, the stuff we're made of,
the ability to preserve organs for transplantations,
and even bring us back.
Back from the dead. Came back to life?
Oh, yeah. We are going to a topsy-turvy world where heat is the enemy.
Heat is like noise.
Random energy and vibration that disturbs and destroys.
But if you get things really, really cold, you can listen to what nature is whispering to you.
So cold that ordinary physics breaks down and the rules change. Things levitate. We will travel to a place so cold that new states of matter are born, where cold is creating a new breed of computers, a quantum leap beyond the most powerful today.
By the time you get to about 500 bits, you have more possibilities than there are atoms in the visible universe.
I'm David Pogue. Join me tonight as we journey down the thermometer.
This is the coldest spot in the universe right now.
It's amazing. I want to get its autograph. To make stuff colder. I'm beginning my voyage down the thermometer from a very warm place in the universe, Earth. Now, you may think it gets pretty cold here. The lowest temperature ever recorded was minus 128 degrees Fahrenheit in Vostok, Antarctica in 1983. But that's a heat wave compared to Saturn, Pluto, and most of outer space. We'll get a lot colder than that as we journey down into the weird world of cold towards absolute zero. But I'm getting ahead of myself. Our first stop is one we can all relate to, 98.6 degrees, the temperature of my body before I came here.
We're gonna go into the chambers.
The chamber? It sounds ominous. Turns out, to learn about the cold, first I have to get hot. 82.9 degrees? That really doesn't sound so bad.
We're gonna put you a little hotter than that.
John Castellani is a scientist at the Army's Doreo test chamber.
Yeah, so this is our environmental chamber.
This gigantic room is designed to recreate every conceivable environment that a soldier might face, from the frigid mountains of Afghanistan to the 120-degree deserts of Iraq.
Wind, humidity control.
In order for this place to work, there's one more thing they need: volunteers. Will we be seeing one of these poor victims?
The only victim that we're gonna see in here today is yourself.
Castellani enlisted me to help test ways of keeping soldiers cool in the heat. To do this, they'll need to track my vital signs.
For core temperature, you'll be using this rectal probe.
Rectal probe? Look,
It may feel a bit uncomfortable, but
no kidding!
all the way past to ensure it doesn't fall out.
How about you just go in there and tell you how hot I am? Pretty hot!
This is mostly for your safety.
Oh, thanks for thinking of me. Next, they outfit me in 40 pounds of body armor, and then it's into the chamber.
It's 104 degrees in here.
104?
Yes.
Did I get a little lemon? Within minutes, my temperature is going up. Dude, what is that, an hour?
Actually, been about 4 minutes.
Their heart rates will start to rise, their core temperature start to rise. For core temperature, it's around 101.5 degrees Fahrenheit. Eventually what will happen is they'll become a heat exhaustion casualty.
After 2 hours, I called it quits.
Please tell me there was some valid scientific purpose for that.
There is. I mean, really what we're trying to understand is when we develop this kind of gear is can we develop it in such a way that we can allow the body to be able to get rid of the heat.
Oh, man.
And why did I get so hot? Because of some basic laws of physics, which I seem to have missed in my high school science class. For example, what is heat? What is temperature? And what is cold?
What did they teach you?
Heat is energy.
Disorganized energy.
The vibrations of molecules.
The motion of atoms.
The faster they move around, the more energy they have. That's heat. Temperature is a measure of how much heat energy they have.
Temperature is measuring the motion of atoms.
Okay, so heat really is something. It's energy, motion, and you can measure how much of it you have.
More and more heat, your temperature goes up.
But cold is another story.
There's no cold flow, it's heat flow.
Really?
You take heat out, your temperature goes down.
You mean you don't put cold in?
No.
Oh.
No, there's really no such thing as cold.
So cold is just the absence of heat? So things don't ever really get colder?
No, they just get less hotter.
Yeah, that has a great ring to it. Making stuff less hotter. That just seems backwards.
So I have a spoon here for you.
Castellani showed me that how we think cold works
Rushing right into my flesh.
can really be the opposite of what's happening.
Actually, the heat from your hand is moving into the spoon, not the other way around. Heat moves from areas of hotter temperatures or high energy to areas of lower temperature or low energy.
You can see it through the eyes of this thermal camera, where warm things like my hand show up as light orange, and colder things like the spoon are dark. And sure enough,
Now, if you put your spoon up against your hand, we can see heat's going from your hand into the spoon.
That's crazy.
the reason I was getting so hot on my forced march was the air was hotter, at a higher energy state than my skin. So instead of the heat from my core flowing out to the room, the heat from the room flowed into my core. The Army has a cool solution.
So David, this is how we're gonna cool you off. So what this is a cooling garment, is essentially gonna circulate water through here. We're gonna hook this up to a small refrigerator.
Ooh, I just got chills.
And keep it at about a nice cool 70 degrees.
I don't know, but I've been told.
I don't know, but I've been told.
104 degrees gets old.
104 degrees gets old.
I don't know.
Just like last time, my core temperature rises in the 104-degree environment. But this time, the heat's got somewhere to go. Into the vest and out through the refrigeration unit.
Significant difference, 82 degrees Fahrenheit, compared to last time when it was up around 95 or 96 degrees.
Best is best if it is cold.
Best is best if it is
He's
cold.
feeling better, he seems in better spirits, and those are all the benefits that we see with this particular technology.
An hour and a half later, as they remove my Kevlar vest, that dark blue area, that's my chest. 78 degrees. Cool, baby. But this is just the beginning of what Castellani has in store for me. 41 degrees. That's the temperature in the chamber as ice water rains down on me.
So Dave, we're gonna do this for 10 minutes.
10 minutes.
So to kind of give you an idea what's going on with you physiologically right now.
I know what's going on with me physiologically. I'm turning into an ice cube.
Yeah.
Castellani and his colleagues developed this procedure not to torture folks, but to solve a mystery. In 1995, a squad of Army Rangers waded through a swamp in Florida. Within hours, 4 died of hypothermia. Yet the temperature was 59 degrees. To understand why they died in such temperate conditions, the Army developed this experiment.
So we're gonna have you get back on the treadmill.
What?
So, after my cold shower, a 30-minute march in 15-mile-an-hour wind.
To mimic again, you're outside.
He repeats this
And we're gonna have it rain on you again.
over and over.
Suddenly I'm dreaming of the days when it was 104.
Their investigation discovered that it was this combination of wet, cold, and wind that killed the Rangers.
So if you were, say, in 50-degree water and immersed to the chest, that water is conducting so much more heat away from you than would air.
I can see that.
Their research established safety guidelines for troops in the cold.
We may be able to tell people, you may be able to last maybe an hour or an hour and a half in those kinds of conditions.
What are the early onset signs of hypothermia?
Well, certainly very intense shivering.
Check.
Changes, for example, a person's ability to walk or their gait.
What?
They start to grumble, they start to mumble.
The test is designed to go on for 6 hours. But after just an hour of this, it was time for my career as an Army test subject to come to an end.
I think we're going to call it quits now, okay?
So far, I've learned how deadly hypothermia can be. But as I continued down the thermometer to our next stop, 91.4 degrees, I'm about to discover that sometimes the opposite can be true.
This is actually a device to induce hypothermia in patients.
Excuse me? Have you never heard of first do no harm? Hypothermia kills you. Dr. Cliff Calloway is a professor at the University of Pittsburgh.
But there are situations in which hypothermia can be beneficial. For example, patients after cardiac arrest.
Patients like Susan Copen, a mother of 3. A few years ago, she set out for a run with friends.
It was a beautiful Sunday morning in November.
She had no idea what was in store.
We're about 2 miles into the run
when a heart valve suddenly failed.
I put my hands on my knees and then collapsed on the sidewalk.
Her heart stopped.
I was gone.
Cardiac arrest. Paramedics arrived. They were able to stabilize her and transport her to the hospital.
Fortunately, Calloway and his colleagues were there. Their goal? To stop the brain damage that immediately follows cardiac arrest.
She was in a coma. We used cooling blankets for hypothermia therapy.
To prevent permanent brain damage in the aftermath of cardiac arrest, they dropped her body temperature to 91 degrees. 2 days later, they warmed her back up. And soon after,
came around and talked to her husband for the first time.
I said,
"Where am I?"
You're in Shadyside Hospital, honey. You never made it home from your run on Sunday.
A year later, she had fully recovered.
The hypothermia treatment saved my life, saved my brain, and I'm a mom and a wife like I was before.
The procedure that saved her life is called therapeutic hypothermia, and I'm about to discover how it works.
Therapy started.
I recognize her. She's the lady on the Star Trek Enterprise.
This device has water coming in through this tubing and pulls heat out of your body.
It's very cold. Just like the Army's cooling vest. But here, in order to fight brain damage, Calloway brings down body temperatures to 91 degrees.
It lowers the metabolism, it reduces brain swelling, it reduces the likelihood of having seizures.
This has proved remarkably effective.
The odds of waking up are almost 2 to 3 times greater for the patient with hypothermia treatment compared to the patient without.
But amazingly, in North America, only 40% of cardiac arrest patients get this treatment. Wait, it triples your chance of survival, but only 40% of patients get the treatment?
Yeah, it's disappointing. We really wish it was done more reliably for more patients.
Yeah, me too. But there's a limit. His treatment can save only the fortunate few cases where paramedics bring back a heartbeat within minutes. Many trauma patients die on the way to the hospital. But biochemist Mark Roth says he has a way to save many of them by getting colder, a lot colder.
Well, a simple way to think about, David, is that we're trying to take the emergency out of emergency medicine.
For years, he's been trying to develop a method that could one day buy trauma patients time by dropping their core temperatures down as far as 60 degrees. The problem is that when people get that cold, it usually kills them. Usually.
There are these outliers.
He believes the answer to saving thousands of lives lies within these mysterious cases. Cases of people who suffered hypothermia so severe it stopped their hearts, and yet they came back to life. Consider the case of Janice Goodyer.
To the brink of death and back.
Her heart stopped. She was unconscious in the freezing snow for 4 hours.
She was brought to the hospital. 24 hours later, walked out of the hospital refusing any treatment and has been fine since.
Her core temperature dropped to 70 degrees.
Another example, Erica Nordby in Canada.
A 1-year-old, her core temperature dropped to 61 degrees after she wandered into freezing cold weather wearing nothing but a diaper.
They didn't find her till the morning.
After 2 hours without a heartbeat, she too was revived.
And also made a full recovery.
But no one's gotten colder than Anna Begenholm.
Has the record for the lowest core temperature of 56.7 degrees Fahrenheit.
She was skiing down a waterfall gully near Narvik in North Norway when she fell headfirst into a river.
Clinically dead for 3 hours.
3 hours?
Right.
It took doctors 9 hours to revive her.
She came back to life?
Oh yeah. Oh yeah.
Anna Borgenholm is back at work and well enough to be with us.
In each of these cases, their hearts stopped beating for hours, yet their brains weren't damaged by lack of oxygen.
How do the exceptions come to be? There must be some way to exist out there and not require oxygen. There has to be, or these people would be dead.
He's searching for a way to do the same for trauma patients, curb their demand for oxygen and not damage the brain by cooling them way down. But there is a big problem.
If you're trying to use the cold to create medical benefit, there's a sort of fundamental problem. Mammals fight that, and they make heat, using up resources in your body in order to do that.
As I discovered when I was shivering in the Army's test chamber, when people get cold, their metabolism actually increases, and they burn more oxygen to make heat. That's what killed the Rangers in the swamp. As they fought to stay warm, their bodies burned through all the available calories, starving their brains of oxygen.
Because that's the fuel that once you burn through it, you are dead.
Roth knew that the reason that Anna Begenholm and the others survived and the Rangers didn't is that they were able to somehow shut off their body's demand for oxygen. But how could he do the same?
So how do I do that? That was a real puzzle.
The answer came to him one night while he was watching TV.
While sitting on my couch at home, watching a Nova show about a cave in Mexico, they said cave air had a little bit of hydrogen sulfide in it.
So we wear these gas masks to help filter out the hydrogen sulfide.
And she said that if you go in there without this respirator, then you will collapse to the ground. Immediately thought, that's it.
He thought that hydrogen sulfide might just be the key. He knew that it naturally occurs in small quantities in the brain where it helps the cells regulate oxygen consumption. But he also knew that too much of it overwhelms the cells, turning off their ability to absorb oxygen, starving them. He wondered if he added just a little to the air to increase the amount in the brain by just a minute quantity, that instead of starving the brain, he could drastically reduce its need for oxygen. He tried it on mice.
Room air laced with hydrogen sulfide.
After 3 hours, its core temperature drops almost 30 degrees.
The mouse is hovering now at about 70 degrees Fahrenheit.
Usually, the mouse would fight the cold and burn through its supply of oxygen.
The mouse no longer responds to cooling by making heat. It actually just gets colder.
Because of the hydrogen sulfide, its brain's demand for oxygen has dropped by 90%.
An animal in this state would survive otherwise lethal oxygen deprivation.
Roth thinks that he can do the same for people. The goal is to clinically duplicate the miracle that saved these people's lives by delivering hydrogen sulfide intravenously. And if he can do that, he will revolutionize emergency medicine and save thousands of lives. It seems the farther down the thermometer we go, the more potential cold has for saving lives. So why stop at 60 degrees? Why not get even colder? To freezing, like in the movies.
Suspended animation.
Yes, suspended animation.
It's inevitable.
To make human time capsules.
Powers volunteered to have himself frozen
or to travel to another solar system.
I've tucked my crew in for the long sleep.
But there's a reason this is called science fiction. The human body is about 60% water. And when water changes from a liquid into ice, the molecules stop moving around freely and lock together to form crystals. And that destroys cells. So far, no one has been able to get around that problem with people. But there is a creature that has.
So we find it generally under the leaf litter.
Cryobiologist John Costanzo studies an animal that has beaten the problem of freezing.
Hey.
The North American wood frog.
Got him.
Some of these animals can, in fact, survive the freezing and thawing of their body fluids.
Back at his lab, he pulled one out from a deep freeze.
Let's go take a look.
Whoa. Oh, man.
There's no heartbeat. There's no brain waves.
A dead frog.
No.
It's frozen. It's a brick of ice.
It's very much alive.
If there's no brain activity, it's dead.
Clinically, perhaps, but we've seen them thaw and come back to life.
How would that be possible?
Ice destroys cells, right?
This frog has worked out a number of different ways to avoid that kind of damage.
The frog's vital organs shrivel up, releasing their water safely away from the frog's organs. And something else happens.
Most importantly, as soon as the frog begins freezing, the liver begins producing compounds that allow the cells and tissues to survive.
A kind of antifreeze, or as Costanzo calls them,
cryoprotectants.
Cryoprotectants.
Huge quantities.
Which protect the frog until the spring, when something amazing happens.
The ice begins to melt, and the water returns to its usual location, so the cells take the water back up. And after a time, the heart begins beating again. We don't know how this happens. It just spontaneously resumes beating.
That's crazy.
That's one of the first signs that the frog is really not dead at all. It's alive. And then the frog begins to breathe. Eventually, the frog will be able to move its limbs, sit upright, and eventually it can hop away.
With these cryoprotectants, the frog has survived the cold of winter. If we could figure out a way to do this for people, we could save lives, not by freezing our bodies, but by preserving our organs for transplantation. That's because organs, even on ice, have a limited shelf life. Hearts, for example, last at most 6 hours. Thousands of people die each year waiting for an organ.
But could we not just inject these cryoprotectants into our bodies?
Unfortunately, it doesn't work that way. Some of the cryoprotectants that these frogs use are very toxic to mammalian muscle tissue.
So how to come up with a similar chemical for human organs? That's the problem researcher Greg Fahey is trying to solve.
The ultimate goal is to be able to set up real banks of organs so that they can be moved anywhere, ready to be plugged in within a couple of hours' notice.
After years of work, he thinks he may have come up with a cryoprotectant that's safe for mammals.
Like the chemicals that the frog uses, we have optimized this particular mixture for the mammal over the last 30 years or so.
With this mixture, Fahey has successfully preserved rabbit kidneys at below freezing temperatures. He starts by removing as much water as possible.
So the kidney might start off being 80% water. We're going to reduce it to about 30% water.
All right, so water out, antifreeze in.
Yes.
The antifreeze is the key. It's called M22, a strange substance that's not toxic to rabbits or humans.
And as you can see at room temperature, it's clearly a liquid.
I imagine M22 must, of course, work better than M20 and M21 did.
Well, M22 is named because it's intended to be used at minus 22 degrees Celsius, which is minus 8 degrees Fahrenheit.
And when they take it down below those temperatures, it behaves strangely.
Cooled to below minus 100 degrees Fahrenheit.
Whoa!
And it's now like a viscous syrup.
Pump this into a kidney, and no matter how cold the organ gets, it won't freeze. How does that work? Unlike solid ice, where molecules are tightly organized, Fahey's cryoprotectant remains liquid no matter how cold it gets.
At a certain point, there's insufficient heat energy in the system to maintain molecular motions, and the system just locks up as a solid, but it's not a frozen solid. We're going to a very different kind of solid state.
So it's a solid, but it's not ice.
It's called a glassy solid state, sort of like a window pane.
So it's not called freezing organs.
You're vitrifying those organs.
Vitrifying. It took them about 4 hours to bring the kidney into this state.
This is now solid. The kidney and the solution surrounding it is at a temperature of minus 190 Fahrenheit. It is a solid glass through and through.
Frozen only in time.
It's just like it was in the liquid state. The only difference is that nothing in the liquid can move anymore. And of course, if nothing can move, nothing can change. If nothing can change, then you have perpetual preservation.
Forever?
Well,
100 years?
Forever as far as you're concerned.
Fahey and his team have successfully re-implanted one of these kidneys into a rabbit.
And we believe that we can put any organ into a vitrified state with enough effort and time.
By making organs colder without actually freezing them, he hopes to make organ banking a reality.
If we can do that, then that organ can wait as long as it takes for the right person to come along who needs it.
From cooling soldiers and saving heart attack victims to preserving organs, the cold has amazing potential. And as I continue my journey down the thermometer, moving from the world inside us to the world around us, I'm headed to the last place you'd think anyone would want to make colder. Fairbanks, Alaska. I trekked there to find out why. Life here seems to revolve around snow and ice, whether it's just playing or beautiful works of fine art.
He's very handsome.
And while snow blankets the ground from early fall to late spring, much of the earth underneath stays frozen year-round. It's called permafrost, but there's a big problem. It's not so perma. When you put a heated building on it, or even an asphalt road, permafrost melts.
It wasn't always wavy like this?
Oh no, when this road was first constructed, it was perfectly level.
Houses are sinking into the ground.
You can see that many of them are not particularly level.
And this doesn't just happen overnight.
No, of course not. It started, what, probably 40 years ago, maybe 30-some. No one ever thought it would get like that.
You must have noticed that things were tipping a little bit. Your coffee cup would slide across the table.
Well, it wasn't that extreme because anyone's common sense would level the table, no matter what condition you're in.
Good point. But what exactly is permafrost anyway?
Watch your head.
Dan White of the University of Alaska, Fairbanks.
Whoa!
Took me underground to find out.
Welcome to my lair, Mr. Pond.
This tunnel is the Army and University of Alaska's Permafrost Joint Research Facility.
Everything here is permafrost.
When it comes to building houses and roads, there are two different kinds of permafrost.
Gravelly materials.
The kind you can build on.
If you had a building, a road on top of this, and you thawed that out, it would remain stable.
The other kind of permafrost is the problem.
Fine-grained soil.
Which gets its structural integrity from frozen water that acts as cement.
So long as it's in the frozen state, you can see that it's structurally sound. You can build roads or bridges or houses on something like this.
Mm-hmm.
The problem, though, is that once it warms up, it turns into this.
A scientific principle we call melting.
Melting, yeah, exactly.
And it's only going to get worse as global temperatures rise. So how to stop it?
We use these thermosiphon devices.
Thermosiphons. Ed Yarmak is chief engineer with the company that invented these things.
Well, it's pretty simple. It's just a tube.
Here's how it works. First, you put some liquid in. Next, you suck out all the air to create a vacuum. Then, you get something cold.
I've got a little Fairbanks snow.
Remember how things always move from hot to cold? Well, because the snow is colder than the air in the room.
Whoa! It's going nuts! Whoa.
The cold draws the heat from the room into the tube, and...
It's cool to the touch, it can't be boiling.
Why is it doing that?
Your boiling point is dependent not only on temperature, but on the pressure inside your tube or in your system.
Because it's in a vacuum, it can boil at room temperature, moving the heat from the room into the snow. Okay, got it, but how in the world is this going to save the permafrost? Well, when you place one of these in permafrost, the heat from the permafrost moves into the thermosiphon. One doesn't think of permafrost as having heat.
Everything has heat, David. In the wintertime, the permafrost is warmer than the air above it. And we all know that heat goes from warm to cold.
Okay, so the heat from the permafrost moves into the thermosiphon. The liquid inside boils, turning into a gas, which rises up, carrying the heat with it. When it gets to the surface, the heat moves out into the colder air. So it stops thawing.
Exactly.
And that works? It's true. In Fairbanks, you can see them around buildings, in roads.
And along the 800 miles of the Alaskan pipeline, you'll find 124,000 of them. Okay, so right now, the building's heat would be thawing the permafrost, except that these devices are sucking the heat out, right?
Exactly.
Blasting into the colder air. But I found a problem with your system. In the summer, the air out here is not cold, so it would not be sucking heat out. I've got you.
Well, in the wintertime, we supercool it, so to speak.
So that it'll have excess cold for the summer?
Exactly. All summer.
Okay, well, what evidence do I have that it's actually working?
You can use this thermal imaging camera.
Oh, wow! They're glowing! You remember the thermal camera. It sees cold areas as darker and warmer areas as lighter. So we can see that there is heat coming out of them thar pipes. But there's only one way to know for sure.
Oh, David, there's other ways to do that.
I'm just kidding. But Fairbanks is hot compared to where we're going. We're plummeting over 200 degrees colder than any place on Earth, where physicists say a whole new world begins. Minus 320 degrees Fahrenheit. That's the temperature of this liquid nitrogen. So much fun. Liquid nitrogen, folks. The ultimate in cold!
Actually, nowhere near the ultimate in cold.
Physicist Eric Cornell knows cold.
Liquid nitrogen isn't even close.
He and his colleagues won a Nobel Prize for using it to discover a new state of matter. Cornell says we're headed to a place so cold that someone had to invent a whole new thermometer just to get there.
Yes, Kelvin, an entirely different one where zero really means something. The bottom, the very lowest temperature you can get to. We call it absolute zero.
But this has a zero on it, so check this out. Check this out.
Yeah. It went down to zero, and look, I've got an amplifier goes up to 11. Doesn't mean anything.
The Kelvin in the Kelvin scale is 19th century physicist Lord Kelvin, who wondered if temperature is a measure of atomic motion, with less and less the farther down you go, why not make zero the place where all motion would stop? He calculated that would happen at minus 459.67 degrees Fahrenheit, which he made zero on his scale.
A real zero, an absolute zero.
So in the Kelvin world, room temperature would be?
It's about 300.
And water freezes at?
273 Kelvin.
And this liquid nitrogen?
77 Kelvin. Truth of the matter is, compared to where we're going, 77 Kelvin is positively balmy. In fact, as you get things colder and colder, that's actually when they start to get the most interesting.
Indeed. To continue on, we'll need to shed our Fahrenheit scale and replace it with Lord Kelvin's. Then take a rapid plunge down to
4 Kelvin.
4 Kelvin? Where the bizarre property of superconductivity was first discovered.
There's certain materials that when you get it really cold, weird things happen.
Little did I know that the substance that would take us there really isn't bizarre at all.
It's helium.
It's really not that cold, that's the funny thing.
But if we turn it into liquid, it's 4 Kelvin, so really cold.
Melissa Gooch at the University of Houston is about to show me how when certain materials...
Oh, this is a piece of lead.
This is lead.
...get super cold, they start behaving in ways once thought impossible. To do this, she lowers the lead into this tank of liquid helium to cool it to a temperature of 7 degrees Kelvin.
Looks like the temperature is plummeting in the warp core, Captain.
If we keep cooling...
That ordinary lump of lead in there undergoes a transformation.
Is it, in fact, a superconductor?
Yes.
Wait, what is a superconductor? Or for that matter, what's a regular conductor? Conductors are materials that allow electricity to flow through, like copper. Most of the wiring in your house is copper. But copper has a problem when electricity flows through it. Electrons bump around, wasting energy as heat. That's called resistance. A superconductor has no resistance, 0. So the current flows through it without wasting any energy.
This is copper wire that we have in our house normally.
And these are normal light bulbs. But Gooch is going to run much less power through them than normal.
Okay, so we're at 12 volts.
That's only 1/10 of the voltage we use in our homes.
It's not very bright.
That's what we get from the copper wire. Watch what happens when we run the same 12 volts through the superconductor.
From a dull glow to full throttle. So you're getting a lot more out of your electricity.
Getting a lot more out of it.
You're wasting a lot less.
Yes.
Scaled up, that wasted energy just in the United States grid alone could power 14 New York cities every year. But that's just the start. Scientists have been working on harnessing the properties of superconductivity for much more exotic applications.
Now I put the superconductor.
Here at the University of Paris, Professor Alain Secuto showed me something extraordinary that happens when a really cold superconductor meets an ordinary magnet.
Oh, and there is levitation now, you know?
And this little puck is just the tip of the iceberg.
Oh, come on. Let's go.
Back to the future!
I'm actually surfing above the ground.
I'm flying!
And it's more than just fun and games. Engineers in Japan are already scaling it up to create the world's first superconductor maglev passenger train. It flies above its tracks at speeds up to 311 miles per hour. And it's cold that makes it happen. So, what's the trick? You might think that the superconductor is acting just like a magnet.
This is now a magnet?
But you'd be wrong.
It's not like a magnet, because here you have both repulsion and attraction.
So these two disks have repulsion and attraction?
Both.
And that's not how a proper magnet behaves. It can't do both at the same time. The superconductor can, because it warps the magnetic field of the magnet to a point where it attracts and repels at the same time.
It's both directions. It's the watch.
But how is this possible? How do superconductors actually work?
Look at that.
The crazy part is, scientists don't really know. It has something to do with that Q word. Okay, where we're going now, 2 degrees Kelvin. Physicists are unlocking a whole new world of cold, where the laws of nature appear to break down. You again.
Yes. Welcome to my world.
What is this place?
This is a matter menagerie. You know, like in states of matter?
I do know states of matter. Solids, liquids, gases.
No. You've come to like a whole zoo of different states of matter. That is called strange matter.
I'd agree with that.
We think that it only exists in the centers of neutron stars. This one I'm particularly proud of. That is the Bose-Einstein condensation. When we discovered that stuff, I won a Nobel Prize.
Nice. I like how you work that in.
Yeah, well, you know.
How many more states of matter are there?
Truth is, some people say hundreds. Look at that. It's called a superfluid.
Superfluid?
Yes. Give the thing a swirl. What do you think's gonna happen?
When I stir it?
Yeah.
It's gonna go around and around in the bucket.
Give it a shot. Yeah, now a little faster.
A superfluid is a state of matter found at temperatures below 2 Kelvin.
Oh, weird. Now a little faster yet, yeah.
Weird.
And once these get started, they'll swirl forever.
Oh,
That is quantum mechanics in action.
As I'm discovering, quantum mechanics is a kind of physics where the usual rules don't apply.
You can think of it this way. In the ordinary world, you, me, atoms, anything you want, they act kind of like balls, just like these balls here. They bounce, they roll around, they bash off each other. But in the quantum mechanical world, each of the atoms starts to act more and more like a wave. And eventually, the wave of one atom starts to grow into the wave of the other. And before you know it, and you can't tell one from the other. The atom could be over here, or it could be over there. And the cool thing is it could, in some sense, really be both at the same time.
Both at the same time?
Yeah.
I mean, how can something be in two places at once?
It's not something we understand that well either. We just go with it.
No
Quantum mechanics
kidding.
is like that, yeah.
And so we depart for colder places. To see how this quantum weirdness can be harnessed to solve real-world problems. To do that, we'll need to inch closer, 1/10 of a degree, 100th of a degree above absolute zero.
Welcome to one of the coldest places in the universe.
What? In an office park in a Vancouver suburb? Meet physicist Geordie Rose of D-Wave Systems, who claims they've used cold to build the world's first commercial quantum computer.
It's C-3PO's wedding cake.
This is a quantum computer.
And then what does that mean?
You have to rethink the way you think about computers to wrap your head around it.
Remember that quantum strangeness below 2 Kelvin? Inside this giant refrigerator, Rose's team keeps a few atoms 100 times colder, all to harness those weird abilities to make a new kind of computer.
So let me get this straight. This entire company, this entire building, this entire meat locker, this entire $1 million apparatus is all designed just to make that tiny chip cold.
Yes.
What does the cold have to do with the computing?
In quantum mechanics, the properties that we're trying to harness are very easily washed out by the movement of the atoms in the processor. As you go down the plates through 4 Kelvin, 0.7, 0.1, at each stage, we want to remove the wiggling of the atoms so that they just calm down, take a seat on the couch, relax. And when they do that, these wonderful, powerful, magical properties that exist in quantum mechanics blossom out.
Quantum properties like being in 2 places at once. That magical ability allows D-Wave to program their computers in a very special way.
The fundamental piece of information storage in this is a device called a qubit.
Like the biblical measurements?
Very unlike the biblical measurement.
A qubit is the quantum version of a bit, the basic unit of information. In a regular computer, a bit can be either a 0 or a 1. But a quantum bit can be either a 0 or a 1, or both 0 and 1 at the same time. This gives it exponentially more power than a conventional computer, which would use 8 bits just to store a single number between 0 and 256. In a quantum computer, 8 qubits can store all 256 numbers at once.
The real kicker is when you have a lot of these bits. The total number of possibilities doubles every time you add a bit.
So, while 10 qubits can store 1,024 numbers, 11 qubits can store 2,048 numbers. When you get to 100 qubits, you can store 1,267,650,650 septillion,
600 sextillion, 228 quintillion, 229 quadrillion, 401 trillion, 496 billion, 703,205,000.
and 376 numbers.
So by the time you get to about 500 bits, you have more possibilities than there are atoms in the visible universe.
Wow.
What this means is that a quantum computer can tackle problems on a scale beyond any conventional computer. From weather prediction and air traffic control to forensics and finance. Problems on this scale are everywhere and have simply outstripped our abilities to solve them. And though some have questioned their claims, there are buyers. D-Wave's first customer? Aerospace giant Lockheed Martin. Their F-35 fighter plane is incredibly sophisticated.
And we have touchdown! Whoa. This is a fairly software-dependent little plane.
Yes, it's got about 9 million lines of code.
9 million lines of code?
Those 9 million lines of code can land a plane on a carrier, evade enemy radar, and hover like a helicopter. Trouble is, no conventional computer could ever check that software for errors without an army of engineers.
Is it just too many variables to all consider at the same time?
That's exactly right. If you have a million, suddenly you can't manage it with any computer on Earth.
Which is why now NASA and Google partnered to buy a quantum computer too, in hopes of better finding habitable planets and speeding up search.
Can I have one?
How much money you got?
Not enough.
So D-Wave's chip is one of the coldest things in the universe? 1/100 of a degree above absolute zero? Well, we're not done yet. I'm about to meet a scientist who can't be bothered with hundredths or even thousandths of a degree for that matter, AKA a millikelvin.
We are bored by millikelvin. We like to go to nanokelvin. That is
nanokelvin?
Nanokelvin. That would be a billionth of a degree.
A billionth of
absolute zero. It's very cold. It's a million times colder than interstellar space.
It's just about the lowest temperature ever reached. A place so clear and cold, physicists can see the fundamental laws of nature in action. MIT's Martin Zwierlein is going to use sodium atoms to show me how to get there, the final frontier of cold.
Wow. Yeah. And so how do you do that?
So we can start over there at the oven.
The oven?
Step 1, cook up some sodium atoms, the same kind in your table salt, to about 700 degrees Fahrenheit. That way you can separate them.
You want to get single atoms to play with, single sodium atoms, lots of them, a whole stream of them.
Step 2, hit them with lasers.
I know you MIT guys have the reputation of being very smart, but I have a little tip for you. Lasers are hot. You might be a little backwards there.
Yeah, you might think about Star Trek where they kill people with lasers. Turns out here, we cool atoms down with lasers, and they get a recoil from it. Just if you hit a billiard ball with another billiard ball.
In other words, when you hit atoms with just the right amount of laser light, it acts like a little shove in the opposite direction that the atom is moving, slowing it down.
If you look down here, you will actually see the cold cloud right there in the center of the vacuum chamber.
So that glowing star thing? It looks like the sun. It ought to be super, super hot.
No, it's actually extremely cold. Those are a billion atoms cooled to a millikelvin.
1/1000th of a degree above absolute zero. But lasers can get us only so far.
You cannot reach the nanokelvin temperatures just with laser cooling. So we need another technique.
Which brings us to step 3. Get out your coffee cup.
What takes over after laser cooling is what we call evaporative cooling. It's the same thing that happens to your coffee right now, because it's just cooling down. So if you now force it a little bit by blowing on the coffee, you speed that process up. The coffee gets colder more quickly. That's exactly what we do here.
But instead of a coffee cup, Zwierlein uses a cup made of magnetic fields to trap his atoms. Then he blows on it with radiation and lowers the rim of the cup to let the hotter atoms escape.
So now we're going to do this coffee cup cooling. It's going to bring us to nanokelvin. Okay, ready for this?
Yes.
Let's do this. All right. So, can you please switch on this stuff? Do this. This is great. Let's switch on this guy. And then this awesome knob here.
Press the awesome white button.
Fantastic. So that's good. Please press F12.
Always wondered what F12 does.
So you see now the atoms are cooling because the cloud size gets smaller and smaller and smaller. And here you see the temperature drop, 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 drop.
Oh, wow.
It takes a few minutes, but eventually the atoms become so cold, they lose their individual identities altogether and coalesce into that new state of matter called a Bose-Einstein condensate.
Wait a minute. Okay, so
yes,
that's the condensate?
That's the condensate.
But look at the temperature.
Yeah, it's very cold.
177 billionths of a degree. 177 billionths of a degree Kelvin.
This is the coldest spot in the universe right now.
That's
right
amazing.
Here.
So not even in outer space?
No. Outer space is a million times hotter.
Not the dark side of the moon.
No, it's like all hot.
Comets.
Terrible, yeah.
Black holes, nothing. This is it, in this room.
Yes.
That's amazing. I would ask its autograph if I could.
Yeah.
But it's not about setting obscure records. What Svirline is excited about is what these exotic states of matter can teach us about the universe.
Our puff of gas teaches us about the neutron stars. Or, split second after the Big Bang, there was this weird form of matter called a quark-gluon plasma.
A super hot type of matter in the early universe that would give rise to everything we see today.
So you're telling me that this tiny, freezing cold dot can teach us something about enormous, blazing hot stuff.
That's the fun part of physics. It connects these very different areas. The very hot, very cold, everything is governed by the same laws.
Amazingly, what happens at these ultra-cold temperatures is that atoms get so smeared out, their waves start looking indistinguishable from those of super hot particles under extreme pressure. Like those inside the inner core of neutron stars. So dense, a teaspoon of them weighs 10 billion tons. Svirline and others can now simulate substances like this in their labs and probe their mysteries.
That's incredible. And then in a couple more years, you'll finally do it. You'll hit 0.0, absolute zero, and we'll be done.
Yeah, unfortunately, it's never possible to reach absolute zero.
What?
But there's always going to be a little drop of energy sitting around somewhere.
Turns out it's impossible to get to absolute zero because no matter how cold you get, everything has tiny quantum jitters. And where you have motion, even a tiny amount, you have heat. But that's not stopping scientists from getting even colder to explore the fundamental laws of nature and how our universe came to be.
Just the way noise can drown out music, heat is like the noise that obscures things. If you get things really, really cold, you sort of drown out, you damp down all the noise, and you can listen to what nature is whispering to you.
It's uncharted territory. Like other frontiers of science, cold has opened the doors to new worlds, where the dead may get a second chance. The planet can be cooled by clever innovation, and the universe may be made more understandable. The secrets are all around us as we learn to make stuff colder.